All right, hello everyone. This is Dr. Gallenstein here again. Today in this lecture, I'm going to talk about the econometrics of experimental analysis. I'm going to go through and talk about how do we analyze the data from an RCT, from a randomized control trial experiment. How do we analyze it? Okay, I'm going to go through the econometric basics of analyzing data from an RCT. All right, so causal identification in regression analysis. All right, so let's say that we've conducted an RCT. We've conducted a randomized experiment, like I talked about in the last lecture, in the randomization lecture. We have randomly we've randomly selected one group to receive our intervention, and then another group to not receive the intervention. So we've a randomly selected treatment group and a randomly selected control group. Okay. And so we've done our randomization. We did our balancing test to confirm that there's statistical independence. And then we implemented our intervention. We implement our intervention, and then we go back, we collect data afterwards. And so now we have data. We have information about our outcome variable. If we go back to the example from last lecture, we were looking at the impact of fertilizer on farmers' incomes. And so our outcome variable is incomes, and our treatment variable is fertilizer. Our treatment or our intervention is fertilizer. Okay, so now we have data. We have information on farmers' incomes, and we have information on whether or not they were in the treatment group or the control group. All right, so then what we do, the most simple, straightforward analysis is we conduct a simple linear regression model using ordinary least squares, where our dependent variable is our outcome variable. So in this case, it would be income. And we include one independent variable, and that independent variable is a binary variable or a dummy variable. And I'm going to use the letter t here, where t will equal 1 if the individual is in the treatment group, and will equal 0 if they're in the control group. All right, so this is the most straightforward approach. We use a simple linear regression model where we have the treatment variable. T is a binary variable. It equals 1 if they're in the treatment group. It equals 0 if they're in the control group. Okay, if we run this regression model, we estimate this regression model using ordinary least squares, then we will get a coefficient estimate, beta 1 hat. And I'm just going to tell this to you right. I'm just going to tell you straight that from this simple linear regression model, beta 1 hat is equal to the mean difference between the outcome variable for the treatment group and the outcome variable for the control group, which means that beta 1 hat is our estimated average treatment effect on the treated. Beta 1 hat is our ATT hat. And so if you go and you run a regression model that has the treatment variable as our independent variable and the outcome variable as our dependent variable, you run this simple regression model, you will get beta 1 hat, and that beta 1 hat will be equal to the simple mean difference. And you can confirm this. You can confirm this. You can solve it two ways. You can run the simple regression analysis and get your beta 1 hat. You can also go in and you can just calculate what's the average outcome variable for the treatment group minus the average outcome variable for the control group. If you do this mean difference, you'll find that this mean difference is the same as your coefficient estimate. And they're both the estimated average treatment effect on the treated. All right, and we know from the past couple lectures that if there is selection bias, then this beta 1 hat will be a biased estimate of the true beta 1. All right, so beta 1 hat will be a biased estimator of the true beta 1, the true impact, right? We know that the ATT hat will be a biased estimator of the true ATT. So the estimated average treatment effect on the treated will be a biased estimate of the true average treatment effect on the treated if there is selection bias. Even if it's significant, this statistical significance is a different thing. Okay, so if beta 1 hat, and so if we have selection bias, then beta 1 hat will be a biased estimate of the true beta 1. Beta 1 hat is the same thing as our ATT hat. Beta 1, the true beta 1, is the same thing as the true ATT, the true average treatment effect on the treated. All right, so if there's selection bias, then the ATT hat, the beta 1 hat will be a biased estimator. Let's see, I might even correct this. The expected value of the expected value of beta 1 hat will not be equal to the true beta 1. So our beta 1 hat will be a biased estimator of the true beta 1. All right. But now, remember from our last conversation, actually, let me reinforce this. Okay, beta 1 hat is equal to the ATT hat. If selection bias is not equal to 0, then beta 1 hat will be a biased estimator. All right, that means beta 1 hat will not give us an accurate estimate of the treatment effect, even if beta 1 hat is significant, statistically significant. All right. Now, if you remember from econometrics class, selection bias is actually equivalent to missing variables from the regression. Selection bias is equivalent to omitted variable bias. All right, you remember that we can have omitted variable bias, right? And if you remember, omitted variable bias implies that beta 1 hat will not be an unbiased estimate of beta 1. That means that beta 1 hat has not given us an accurate estimate of the true effect. All right. So those omitted variable must be controlled for either explicitly in the regression or through elimination or eliminated through the impact assessment design. All right, and we can already predict that. Think back. In our last lecture, we talked about randomization. If we have randomization and we balance and we have statistical independence, then we won't have selection bias. If we don't have selection bias, we don't have omitted variable bias, which means beta 1 hat will be an unbiased estimate of the true beta 1. All right. All right. Now, there's two methods to establish causation. All right, we need to get rid. We need to get rid of that selection bias. For us to establish causation, we need to get rid of that selection bias. The first way, which we talked about last time, is randomization. If we randomly assign the treatment and we achieve statistical independence, then our selection bias will equal 0, and our beta 1 hat will be an unbiased estimator of beta 1. All right. The other option is, let's say we didn't randomize or our randomization was unsuccessful. That means we don't have statistical independence. Okay. The other econometric tool we can say is we can control for the selection. That means we try to account for the omitted variable bias. That means we would need to control in our regression, we would need to include covariates, other independent variables other than the treatment variable. We would need to include other independent variables that control for all the possible sources of selection bias, all the possible differences between the treatment group and the control group. All right, we would have to include control variables for all the possible differences between the treatment group and the control group. All right, these are control variables or covariates. All right. Now, the problem with this second method is that, and if you've taken econometrics, you probably recognize this. The problem with this second solution is that it is very, very difficult, if not impossible, to include all omitted variables. So the problem is that it's very, very difficult to make sure that you have controlled for all the possible differences between your treatment group and control group. And if you don't, then you're not going to have a causal effect. You will have a biased estimate of beta 1. All right, you'll have a biased estimate of your average treatment effect on the treated. Okay, so the primary way for us to solve this problem is randomization. Now, later in the class, at the end of the class, the last section of the class, we will talk about some econometric methods that we can use to try to solve this problem even when we don't have randomization. But we'll get back to that for later. For now, we're going to we're going to focus on randomization. So we want to randomly assign who gets the treatment and who does not get the treatment. In that case, we can assume the selection bias is 0, and we can say that beta 1 hat is an unbiased estimator of beta 1. All right. Now let's test what we've done so far. So let's say we wish to increase agricultural incomes in Benin. We identify a sample of 1,000 low-income farmers. We randomly assign 500 farmers to the treatment group and 500 to the control group. We provide each farmer in the treatment group a voucher for discounted fertilizer. In this case, we are going to run a regression where we have income as our outcome variable, right? Remember I said we want to know the impact. We want to increase agricultural incomes, all right? So we have income as our outcome variable. And then we have this voucher variable, same thing as our treatment variable. Voucher equals 1 if they receive the voucher, and voucher equals 0 if they didn't receive the voucher. We run this regression. We find beta 1 hat. We find that it's positive and it's significant at the 1% level. Can we conclude that the voucher caused an increase in incomes? Why or why not? Think about it for a second. In this case, we can conclude that it's caused because we have randomly assigned the treatment. We've randomly assigned the voucher. We found that it's positive and statistically significant. All right, so that means there is a statistical relationship between the voucher and income. It's positive, and we know that because it's randomized, and let me assume for now that it's balanced, right? So we have statistical independence. Okay, as long as we have that statistical independence, then we can conclude that this beta 1 hat is the causal effect of the fertilizer voucher on incomes. Why can we conclude that? Because it's randomized. And for right now, I'm assuming that it achieves statistical independence. All right, let's do another example. So let's say, again, we want to increase agricultural incomes in Benin. This time, we give farmers access to vouchers for discounted fertilizer. That means we're not giving farmers, we're not randomly assigning who gets the voucher. We're just making it available. Any farmer who wants the voucher can come and get it. All right, so then we have this voucher variable. It equals 1 if they get the voucher. It equals 0 if they don't get the voucher. We run the regression model. We find beta 1 hat. It's positive and statistically significant. Can we conclude that this voucher caused an increase in incomes? Why or why not? In this case, no, we cannot conclude causation. Why? We cannot conclude causation because the voucher was not randomly assigned. Farmers got to choose whether they got a voucher or not. That creates selection bias. There's going to be some systematic difference between the farmers that chose to get the voucher and farmers that chose not to get the voucher. That means even if beta 1 is statistically significant, it's not causal because there's going to be selection bias. All right, what if we try to control for the differences? What if we include a whole bunch of covariates? We try to include variables that control for all the possible differences between the treatment group and control group. And let's say that we still find that beta 1 hat is positive and significant. Can we conclude that the voucher caused an increase in incomes? Why or why not? In this case, it's a little bit tricky. If we are actually successful and we actually control for all the differences, then we can say yes, it does have a causal effect. The problem is we almost never are able to control for all the possible differences. We almost are never able to assume that we do not have omitted variable bias unless the variable is randomized. All right, unless the treatment is randomized. And so in this case, I would say no. Why not? Because it's very difficult to control for all the omitted variables. Now, like I said, there are some techniques that we can use that can help get around this problem, but I'll talk about those much later in the course. All right. Now, so that kind of gives us an overview of the econometrics, but let me even kind of review something that's even more simple. Remember what I said using the the potential outcomes framework, that my estimated average treatment effect on the treated, my ATT hat, is equal to the mean difference in the outcome variable between the treatment group and the control group. Okay, my ATT hat is literally this. That means the first thing that I can do when I'm analyzing data from an experiment is I can just simply compare the means. I can take the average of the outcome variable for the treatment group, and I can compare it with the average of the outcome variable for the control group. And so, using our previous example, the estimated average treatment effect on the treated will be the expected value of income for people that have the voucher minus the expected value of income for people that do not have a voucher. And this ATT hat will be equal to the true ATT, the true average treatment effect on the treated, plus any selection bias. If we randomize and we achieve statistical independence, then that selection bias will be 0, in which case our estimated average treatment effect on the treated will be equal to our true average treatment effect on the treated. So that means when we have randomized data, the first thing we can do isn't even a regression. It would be just look at the mean difference. We would just compare the averages between the treatment group and the control group. All right, and we would report those results in a table that looked like this. Very similar to the balancing test. Very similar to the table that we have in the balancing test. But this time, we're not looking to see if they're the same on average. We're looking to see what the difference is. If we've randomized and we have statistical independence, that means our treatment group should be the same as our control group on average, which means that any observed difference, any difference that we see between the treatment group and the control group for our outcome variable can be attributed to the treatment. It can be attributed to the intervention. All right, so what we would do is we just calculate what's the average for the treatment group, what's the average outcome variable for the treatment group, what's the average outcome variable for the control group. We calculate the difference, and then we look for the significance. In this case, we find that there's a statistically significant difference of 502, significant at the 5% level. And as long as we randomized and we have statistical independence, then we would conclude that the treatment caused a 502 GONA-CD increase in farmers' incomes. Okay. All right, so let's keep going. Let's keep reinforcing this. So let's go back to our simple regression analysis. And we're just going to reiterate the y, the dependent variable is our outcome variable. Let's use a different, I have here in this slide, I'm assuming a different example. Let's say I'm doing an experiment to determine the impact of textbooks on students' test scores, okay? So the outcome variable is test scores. That means our dependent variable is test scores, all right? We're doing a simple linear regression model, all right? Our t, the t variable indicates whether or not a school is in the treatment or the control group, all right? So that means t equals 1 if the students receive textbooks, and t equals 0 if the students do not receive textbooks, okay? That means beta 1 is the impact of the treatment on the outcome. Beta 1 is the impact of textbooks on students' test scores. Beta 1 equals ATT. Okay. So we run the regression. We estimate beta 1. That's beta 1 hat. Beta 1 hat is our estimated value of beta 1. So beta 1 is equal, beta 1 is the true ATT. Therefore, beta 1 hat is the estimated, the ATT hat. All right, it's the estimated ATT. We know that the ATT hat, the estimated average treatment effect on the treated, is equal to the true average treatment effect on the treated when we randomize, because selection bias is 0. All right, that means our beta 1 hat is equal to the true ATT. No selection bias, no mid-variable bias. All right, so if we run a regression, and let's say this is our treatment variable, we run a regression. If we have successfully randomized, we implemented a random experiment, and we had statistical independence, our sample's balanced, then we would look at this coefficient. This coefficient is beta 1 hat, and we would conclude that this is the true, this is equal, this is an unbiased estimate of the true ATT. All right, so we run a regression. This coefficient here, this is beta 1 hat. This is equal to the estimated average treatment effect on the treated, the ATT hat. All right, we would report that in a regression table, in a nice clean table like this, 0.12, okay? And this variable here, this coefficient here, this is beta 1 hat, and it's equal to the ATT hat. All right. If we randomized and we have statistical independence, then we would then conclude that this is the true average, this is an unbiased estimate of the true average treatment effect on the treated. Okay. All right, so now let's talk about the issue of covariates. That means other variables. That means other independent variables in my model other than the treatment. When would I include covariates? When would I include control variables, other variables? All right, there's 3 reasons why I would include covariates in my regression model. The first reason is that if I include covariates, that will reduce my standard errors. That increases the precision in the estimates. That increases the chances that I will find that my beta 1 hat will be statistically significant. All right, that reduces the chances of committing a type 2 error. All right. Another option is that I might include covariates if I want to check for heterogeneous treatment effects. If I want to do a subgroup analysis, I might just clarify this. I want or to measure, let's see, I want to conduct a subgroup analysis. Okay. All right, and then lastly, I would control covariates if my randomization wasn't perfect. You know, if I did my randomization and my samples didn't balance, then I might include all of the variables that didn't balance in the regression. Okay. All right, let me go into those more in detail. All right, so 3 reasons why I would include covariates or other independent variables. The first is to reduce the standard errors, improve the precision. So covariates that are correlated with y will reduce the standard errors and improve the ability to find a statistically significant beta 1 hat. Covariates in the analysis of RCTs should be pre-treatment variables. That means they should come from the baseline survey. That means that they will be unaffected or uncorrelated with the treatment. All right, and so those should have no impact on the placement of the treatment. All right. All right, the second reason is we might want to measure heterogeneous treatment effects. We might want to look at a subgroup analysis. We might want to try to find what is the impact of the treatment on some subgroup. All right, we might want to say, well, what's the impact of the treatment on men versus women? Does the treatment have a different impact on men as compared to women? All right, we might want to do that, and if we do that, we would need to include some covariates. I'll go more into detail on that in a minute. Lastly, I might want to include covariates if my randomization fails to achieve statistical independence. So if I randomly assign my treatment and I do my balancing test and I find that my sample does not balance, so there's not statistical independence, I would take all of the variables that didn't balance and I would include them in my regression. Okay, so those are the 3 reasons. All right, so just review here. T1. This is, T, that's my treatment variable. Beta 1, that's the average treatment effect. All right, I'm trying to get an estimate of beta 1. Other variables here are covariates. They're other independent variables. All right, if my randomization is successful, that means if I have statistical independence, that means covariates are not necessary. I don't need to include them. However, like I said before, I might include them if I want to reduce the standard errors, which means reduce the type 2 error. I might include them if if I do not have perfect balance. That means if I do not have perfectly successful randomization. or I might include them if I want to do a subgroup analysis. All right. Now, when I'm reporting results, when I run analysis of experimental data, the first thing I will do is I'm going to run a model that has only the treatment variable in it. This is the simple regression model. All right, so I've just given you an example of it here. Model 1 has only the treatment variable in it. Okay? And then I'll run a second model that includes covariates, other independent variables. So in this case, model 2, and model 2 is going to have the treatment variable, and then it's going to have a bunch of other covariates. Okay. This treatment variable, the coefficient on the treatment variable is going to be, it's my beta 1 hat, and it's going to be my estimated average treatment effect on the treated. Okay. All right. Now, if my randomization is successful and I have statistical independence, then when I introduce these other covariates, these other independent variables, my coefficient, my beta 1 hat, my coefficient on the treatment variable should not change very much. It should change very little. That's what you find here. That's what you see in this example. The coefficient changes very little. If you remember from econometrics class, if you have omitted variable bias, then when you add additional variables, your coefficients will change. All right? That's the same thing that we see here. If we do not have selection bias, that means if we have a successful randomization, we won't have selection bias, which means we don't have omitted variable bias, which means when we introduce new variables, the coefficient on the treatment variable should not change. It should not change. All right. And so if you introduce new variables and you find that the coefficient on your treatment variable does not change very much, changes very, very little, that is a good indication that you have a successful randomization. That is a good indication that your sample balances. That's a good indication that you are identifying your treatment effect. However, if when you add additional variables, you see that the coefficient on your treatment variable changes, this is a good indication that you do not have statistical independence. This should throw up red flags. If you introduce new variables and your coefficient changes a lot, that is a red flag. That means something's wrong. Your randomization, you do not have statistical independence. That means that in model 1, you had omitted variable bias. That means we have selection bias. If you see this, then you would say, okay, I don't have a good randomization, I don't have statistical independence, and that means that I cannot conclude that I have the causal effect. I cannot conclude that this number, that this coefficient is the causal effect of my intervention. Okay. All right, the last thing I'm going to go over here is subgroup analysis. How would I conduct a subgroup analysis? Okay, I mentioned this before. One of the reasons why we might include covariates or other independent variables is to conduct a subgroup analysis. Okay, let me be clear. What is a subgroup analysis? A subgroup analysis is when I want to know the effect of my treatment on some subset of my sample population. So a common example might be, let's say I have a sample of 1,000 farmers, and I want to know the average treatment effect on all 1,000 farmers. Okay, but I also want to know what's the treatment effect on the male farmers and the female farmers. Does the treatment have a different effect on male farmers versus female farmers? A subgroup analysis is what I would do to figure out whether or not my treatment has a different effect on one subgroup, male farmers, versus another subgroup, female farmers. That's a subgroup analysis. What is the effect of my treatment on those different subgroups, a subgroup within my sample population? I might just add a little tangent here. If I know that I want to conduct a subgroup analysis, I will stratify by that subgroup. So let's say if I know in advance that I want to I want to find the treatment effect. I want to see if there's a different treatment effect between men and women. If I know that I want to do that in advance, then I will stratify by gender. Let's say I want to know I want to do a subgroup analysis by education. I want to know, does my treatment have a different effect for really well-educated people compared to poorly educated people? If I want to know that, then I would stratify by that variable. I would stratify by education level, and I would say, okay, I'm going to stratify. Half of my sample will be in the high education group, and the other half will be the low education group, and I'll randomly assign my treatment within those strata. All right, so that's just kind of tying this into the last lecture on stratification. All right, so let's do it. Let's say I want to do a subgroup analysis where I'm looking at the difference in my treatment effects between men and women. What I'm going to do is I'm going to run a regression that looks something like this. All right. This regression has my treatment variable, just like before. It's also going to have a covariate, another variable, another independent variable, where this independent variable indicates the subgroup. So if I'm doing gender, then this X variable is going to be gender. It'll equal 1 for women and 0 for men. Okay? And then I will include the interaction term. The interaction term is when I multiply the treatment variable by this variable X. I multiply the treatment variable times the gender variable. All right? So I run a regression that has the treatment variable, the variable that indicates the subgroup, and then the interaction term. Interaction term, an interaction between the treatment and X. So let's say X is gender. That means X equals 1 for females. All right, so what this does, this implies that my average treatment effect on the treated, my estimated average treatment effect on the treated, is no longer beta 1 hat per se. My estimated average treatment effect on the treated is now beta 1 hat plus beta 3 hat times X. Now, if you remember from calculus, you can get this by taking the derivative. If you take the derivative of this regression model with respect to t, that will give us our average treatment effect on the treated, or estimated average treatment effect on the treated. Okay? The derivative of this model with respect to t will be beta 1 plus beta 3 times x. All right, so then our estimated average treatment effect on the treated will be equal to the estimated beta 1, so beta 1 hat, plus beta 3 hat times x. Okay, now this is going to allow us to determine the average treatment effect on the treated for females and the average treatment effect on the treated for males. All right. How do we do that comparison? How do we know what's the treatment for females and what's the treatment for males? What's the effect on females and what's the effect on males? Okay. What we do, we can just look at this equation. So this is your secret. This is the secret tool. This is the equation. All right. For females, x equals, all right, for females, x equals 1, right? I said that over here. X equals 1 for females. So that means that if I want to know the effect of the treatment on females, then I would set x to equal 1, which means the effect of the treatment on females is beta 1 hat plus beta 3 hat. All right? Now, if I want to know the effect of the treatment on males, I would set x equals 0, right? So x equals 1 for females, x equals 0 for males. So that means x equals 0. All right? Beta 3 times 0 is 0, which means the effect of the treatment on males is just beta 1 hat. This implies that beta 3 hat is a measurement of the difference in the treatment effect between males and females. All right? This is how I conduct a subgroup analysis, is I run this regression. And then how do I analyze the coefficients? I look at the coefficients this way. The average treatment effect on the treated for females is beta 1 plus beta 3. The average treatment effect of the treatment for males is just beta 1. Okay. All right, so what does this look like when I report the regression results? So let's say model 1 has just the treatment variable. Model 2 has the treatment variable and the interaction term. All right, so then let's do the illustration. What's the treatment effect for females? Okay, the treatment effect for females will be beta 1 plus beta the beta 3, or the beta on the interaction term. So that means it's going to be 398 plus 116. That'll be 514. Then what's the treatment effect for males? Well, that's just beta 1. All right, so that's just beta 1, which means the treatment effect on males is 398. Okay, so we can see that equation here. Now, I want to make one quick note here. I mentioned before, and I really stress this, if my coefficient changes when I add covariates, that is an indication that I have selection bias. All right. But that's a different story, but it's different when you introduce an interaction term. You would expect the variable, the coefficient on the treatment variable, to change if one of those covariates is an interaction term. So this is not a problem. This is not an indication of omitted variable bias because we're including an interaction term. If you wanted to see if you wanted to look for evidence of that omitted variable bias, then run model 2 without the interaction term first and see if the coefficient changes. Okay, so that finishes the first run through of econometric analysis of experimental data. I hope that you enjoyed the lecture. Let me know if you have any questions, and have a great day.